Okay, in this video here, we're going to be looking at sequences again. Specifically, we're going to be looking at recursively defined sequences. We'll look at a little bit of factorial, just to give a little bit of a review of factorial. Sometimes it's, usually it's covered in pre-calculus a little bit. We'll see factorial a lot later on, and so we'll do a little bit of basics of factorial. And then we'll look at arithmetic and geometric sequences. So a recursively defined sequence is a sequence whose first few terms are given and the subsequent terms are defined using the previous terms. So a very famous recursive sequence is called the Fibonacci sequence. And the Fibonacci sequence doesn't have to be defined with a 0. It could be defined as a1. So oftentimes the first term of the sequence is ace of 0. So ace of 0 and ace of 1, the first two terms are going to be defined as 1. And ace of n is going to be equal to the previous two terms. So ace of n is equal to ace of n minus 1 plus ace of n minus 2. So the previous two terms. And of course we got to do that for n greater than or equal to 2. So starting with the third term of the sequence, you start adding the previous two. So we're going to write out a number of terms of the Fibonacci sequence. So the first term is 1, second term is 1. The third term is going to be the sum of the previous two terms, which both happen to be 1. So 1 plus 1 is 2. The fourth term of the sequence is going to be the sum of the previous two terms. So ace of 2 plus ace of 1. So 2 plus 1 is 3. The fifth term of the sequence is going to be the sum of the previous two terms, those being ace of 3 plus ace of 2. So it's going to be 3 plus 2, which is 5. The sixth term of the sequence is the previous two terms, 5 plus 3, which is 8. The seventh term of the sequence is going to be the sum of the previous two terms, so 8 plus 5 is 13. The eighth term of the sequence is going to be 13 plus 8. The ninth term of the sequence is going to be 21 plus 13. And the 10th term of the sequence is going to be 34 plus 21, or 55. And so we can write that out. 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and etc. It's an interesting sequence. Definitely go and Google it. Maybe watch some YouTube videos of where the Fibonacci sequence appears in nature. It's pretty cool. It's a cool sequence. Okay, so let's look at some more recursively defined sequences. So this is example number 13 from the handout, and we're going to show the recursively defined sequence where ace of 1 is 1,000 and ace of n plus 1 is 5, 6, ace of n plus 300 is monotonic and bounded, and find the limit of the sequence. Okay, now there's a problem in the homework that's basically this problem here, but it goes that you have a farmer that has 1,000 acres of land or something, and he harvests 1/6 of it, or I think it's harvests 1/6 of the land, and so there's 5/6 of it left over, and then he plants seeds for 300 more. And so that's where you get the ace of n plus 1 is equal to 5, 6 ace of n plus 300. And so you would have to translate that when doing that problem. So we're going to go ahead and look at what this sequence is doing. So ace of 1 is 1,000. That's what it's defined to be. Ace of 2 is going to be 5, 6, the previous term of the sequence, and then plus 300. So that's going to be approximately 1,133.33, etc. I'm just going to round it to one decimal place. Ace of 3 is approximately 5, 6 times the previous term, 1133.3, and then plus 300. which is approximately 1244.4. And then we could keep going. But based off of this, it appears to be increasing. So if it's increasing, then ace of n should be smaller than ace of n plus 1. Ace of n is less than or equal to, so we're just going to work that out and see if we get a true statement. So ace of n plus 1, by definition, is 5, 6, ace of n plus 300. Okay. So what we're going to do is we're going to subtract 5, 6, ace of n from both sides. So ace of n minus 5, 6, ace of n is going to be 1, 6, ace of n, less than or equal to 300. So ace of n is less than 1800. I think I misspoke here. We're not showing that it's increasing. We're assuming it's increasing based off our observation. So from the fact that it is increasing, we're actually showing that it's bounded from above. And so what we have is a monotonic increasing increasing sequence, and bounded from above. And so that's going to converge. So the limit as n goes to infinity of ace of n plus 1 is going to have the same limit as n goes to infinity of 5 over ace of n plus 1. Sorry, 5, 6 ace of n plus 3. So ace of n plus 1 is, by definition, 5, 6 ace of n plus 3. Okay, now ace of n plus 1 and ace of n are both part of the same sequence, so they're going to have the same limit. So the left-hand side will be L, and the right-hand side will be 5, 6 times L plus 300. We'll go ahead and solve this by subtracting 5, 6 L from both sides. So we'll have 1, 6 L is equal to 300. Multiply both sides by 6, and the limit is going to be 1800. Okay, so that would be our limit there. Now let's look at another example of a recursively defined function, and we'll find a limit. So suppose the recursively defined sequence, ace of 1 is equal to 5, and ace of n plus 1 is defined to be 3 plus 2 over ace of n. And then we're going to make the assumption that it's convergent, and we're going to find its limit. So ace of 1 is going to be 5. Ace of 2 is going to be 3 plus 2 over ace of 1. So that'd be 3 plus 2 over 5, which is approximately 3.4. Ace of 3 is going to be 3 plus 2 over the previous term, which is 3.4. That is approximately 3.59. Ace of 4 is approximately 3 plus 2 divided by the previous term, which is approximately 3.56. Ace of 5 is going to be 3 plus 2 divided by the previous term, which is going to be approximately 3.56. They have a little bit of a different decimal expansion if we go out a little bit further. It does not appear to be increasing or decreasing, but it does appear to be getting stable. So perhaps 3.56, etc., might be the limit. So with rounding, it appears to settle down, but it's not monotonic. But we did make the assumption that it does have a limit. So the limit of ace of n plus 1 is going to be equal to, by definition, the limit as n goes to infinity of 3 plus 2 over ace of n. Because we're assuming that the limit exists and it's L, ace of n plus 1 and ace of n will both go to L. So this is L equals 3 plus 2 over L. We'll go ahead and multiply both sides by L. So L squared is equal to 3L plus 2. And this is a quadratic, so we'll set it equal to 0 and hope it factors. It does not factor, so we're going to use the quadratic formula. Maybe you've heard the silly quadratic formula story. A negative boy is uncertain whether he wants to go to a radical party. So the radical party is the square root. Because he's a square, he misses out on 4 awesome chicks. And the party's all over at 2 a.m., but there's no M in the formula. So maybe you've heard the silly story before. All right, so moving along. This is going to be -3 plus or minus the square root of -3 squared minus 4 times 1 times -2 all over 2 times 1. So 3 plus or minus 9 plus 8 over 2. So 3 plus or minus the square root of 17 over 2. So the limit is either 3 plus the square root of 17 over 2, which is approximately 3.5616, or the limit is equal to 3 minus the square root of 17 over 2, which is approximately -0.5616. So which one is probably going to be the limit is the positive one. Because we're doing 3 plus 2 over a sub n, we're adding positive numbers, so we're not going to ever get a negative number, so we're going to throw out the negative limit there as an extraneous solution. Okay. All right, so let's talk a little bit about factorial. 0 factorial is defined to be 1. 1 factorial is 1. 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 3 times 2 times 1, which is 24. In general, n factorial is n times n minus 1 times n minus 2 times n minus 3, blah, 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 times 2 times 1, all the way down. So we're going to simplify some expressions involving factorial. So let's suppose that we have 5 factorial. That means 5 times 4 times 3 times 2 times 1, which is 120. 2n factorial over 2n plus 1 factorial. We'll end up having expressions like this a little bit later on. So it'll be good to work with expressions like this. So 2n factorial means 2n times 2n minus 1 times 2n minus 2 all the way out to 2 times 1. So just count down from 2n. 2n plus 1 factorial means 2n plus 1 times 2n times 2n minus 1 times 2n minus 2 all the way out to 2 times 1. And what's going to happen is you have the same factors. So you have the factors of 2n, 2n minus 1 and 2n minus 2 with 2n and minus 1 and 2n minus 1, 2 times 1 and 2 times 1. So everything absorbs except for the 2n plus 1 in the denominators. So this simplifies down to 1 over 2n plus 1. So let's do another one very similar to that, but we won't write it all out. So 19, let's look at 3n plus 3 factorial over 3n factorial. So what we're going to do is we're going to write out the larger one until we get to 3n. Okay, so this is going to be 3n plus 3, 3n plus 2, 3n plus 1, 3n, and then we're going to stop it with a factorial. It would keep going 3n minus 1, 3n minus 2, but we have a 3n factorial in the denominator, so that's why we want to stop it. So then the factors of 3n absorb, and this is now 3n plus 3, 3n plus 2, and 3n plus 1. Okay. All right. Number 20, sometimes you see expressions like this in a statistics class or anytime you're doing probability. This is for combination. 7 factorial over 4 factorial minus, 7 factorial over 4 factorial times 7 minus 4 factorial. So if you've done combinations before, this would be 7 and choose 4, or you have 7 objects and you can choose 4 of them to make a group. How many different ways can that be done? All right, so we're going to take the 7 factorial and we're going to write that all the way down to 4 factorial, so it'll cancel the 4 factorial in the denominator. So 7 times 6 times 5 times 4 factorial. Remember, 4 factorial is 4 times 3 times 2 times 1. We just stop it at 4 factorial to abbreviate it. This is all going to be over 4 factorial. 7 minus 4 is 3, so 3 factorial is 3 times 2 times 1. The 4 factorials will absorb. 3 times 2 times 1 is 6, and so we have left 7 times 5, which is 35. Okay. All right, And the last two slides here, we're going to be looking at arithmetic and geometric sequences. So an arithmetic sequence it's going to start out with an ace of 1, and then what we're going to do is we're going to either add the same number or subtract the same number. So we'll just say common difference d, and we're going to add that. So ace of 1, in the next term we would add d to it. Okay, and then in the next term we'd add another d to it. So previous term was a1 plus d, we're going to add another d to that. Okay, previous term was a1 plus d, and we're going to add another d to that. Okay, and so just to get to the next term of the sequence, we add d. So we have this recursively defined. Ace of n is equal to the previous term, ace of n minus 1, plus d. So all that means is to get to the next term of the sequence, take the previous one and add d to it. So a little bit disadvantage of recursive is if I want to know the 100th term of the sequence, I got to know the 99th one, and then I got to know the 98th one, and the 97th one. So if there's a way to get an nth term formula, this is going to be a little bit more convenient. So if we take the a1, comma, a1 plus d, comma, a1 plus d, etc., and we'll rewrite that. That's going to be a1, comma, a1 plus d, comma, a1 plus 2d, a1 plus 3d, etc. So ace of n is going to be ace of 1. That appears in all of them, plus d. And if we want to start here, this is 1, this is 2, this is 3, this is 4, etc. I want to use n minus 1, and that'll accurately describe that. So for the first one, we'd have 1 minus 1, so don't add any d's. Okay, the second term, 2 minus 1, I would add 1d, and etc. So this is our nth term formula. Now, with that, all I need to know is the first term and the common difference, and then we can find the 50th or the 100th term piece of cake. So let's do an example where we're going to find the 50th term. Of the sequence. So our sequence is 1, 3, 5, 7, 9, etc. So this is an arithmetic sequence. We notice that we're adding 2 to each term. So 1 plus 2 is 3, 3 plus 2 is 5, 5 plus 2 is 7, etc. So our nth term is going to be the first term, which is 1. Your common difference is 2. That's what you're adding each time. So ace of n is equal to 1 plus 2 times n minus 1, which simplifies to 2n minus 1. Okay. So if we want to find the 50th term, ace of 50 is going to be 2 times 50 minus 1, or 99. Okay, let's do another example. So 8, negative 1, negative 10, negative 19, etc. So 8 minus 9 is negative 1. Negative 1 minus 9 is negative 10. Negative 10 minus 9 is negative 19. So this is an arithmetic sequence. You're subtracting the same number over and over again. First term is 8. Common difference is negative 9. So ace of n is equal to the first term of 8 minus or plus whatever your common difference is. So minus your common difference of 9 times n minus 1. And that simplifies down to negative 9 plus 17 as our nth term formula. So ace of 50 is equal to negative 9 times 50 plus 17, which is going to be negative 433. Okay. All right. So arithmetic, adding or subtracting the same number each time to get to the next term of the sequence. Geometric, you're going to be multiplying by the same number to get to the next term of the sequence. So we'll look at a geometric. So ace of 1, and then we're going to take ace of 1 and we're going to multiply by r. And then the next term, we're going to take ace of 1 times r, and we're going to multiply by r again. And then we're going to take the previous term, ace of 1 times r, and we're going to multiply by r again, and we just repeat this pattern. So to get the nth term, you need to take the previous term, ace of n minus 1, and multiply it by r. So this has a disadvantage of recursive is to know the 10,000th term. We need to know the 9999th term in order to find the 10,000th term. So maybe we can rewrite this as a1 comma a1r plus a1r squared plus a1r cubed, and see if we can notice a pattern for the nth term formula. And we do. It's a sub n is equal to a1 r, and we don't want the r to be multiplied by the first term, so we do an n minus 1, and that'll describe this geometric series. So we're going to find, instead of finding the 50th term, we're just going to find the nth term formula, and we're going to look at two sequences here. So 1 comma negative 1/3 comma 1 over 9 comma negative 1 over 27, etc. Now, what it appears that is happening is we're multiplying by negative 1/3. Now, one way that we can verify that we do have a common ratio here, what we're multiplying by, is to take two consecutive terms, take the second one, and divide it by the first one. So if I look at 1 and negative 1/3, the second term is negative 1/3 divided by the first term, which is 1, so our common ratio is negative 1/3. Well, maybe I didn't use those two. Maybe I used negative 1/3 and 1/9. The second one is 1/9, and the first one is negative 1/3. Flip and change the sign, and we also get negative 1/3. Or maybe I use the 1/9 and the negative 1 over 27. So the second term is negative 1 over 27, and the first term is 1/9. So negative 1 over 27 times 9 over 1, and that simplifies to negative 1/3. And so maybe a little bit overkill, but we do have our common ratio. So our a sub n is going to be the first term of 1 times negative 1/3 to the nth minus 1 power. We can rewrite this as negative 1 to the n minus 1 over 3 to the n minus 1. And the first form was fine also. Okay. All right, let's do one more. So let's look at the sequence 2 natural log of x, 2 natural log of x, and then the natural log of x squared, 2 times the natural log of x cubed, and etc. So it appears that maybe we're multiplying by the natural log of x each time. So let's check it out. So take the first two terms and take the second one, which is 2 natural log of x quantity squared, just the natural log of x squared, and divide that by 2 times the natural log of x. And so that'll give us natural log of x as our common ratio. Then take the next two, 2 natural log of x squared and 2 natural log of how do I want to say it? 2 times the quantity natural log of x squared, and then 2 times the natural log of x quantity cubed. The quantity cubed is going to be in the numerator and squared on the denominator. And so we end up getting the natural log of x there. So our common ratio is natural log of x. So a sub n is equal to a1, which is 2 natural log of x, times common ratio, natural log of x to the n minus 1 power. We are multiplying like bases, so natural log of x times natural log of x and then to the n minus 1 power, we're going to go ahead and add those exponents. So this simplifies down to 2 times natural log of x, and that's raised to the nth power. Okay, there may be one more video. This might be it for sequences. So if not, we will be getting into 5.2 in the next video. So we'll see you next time.